Hi, this is part 3 in our series on beams. In this section, we're going to look at internal loads inside of beams. So when we put a beam under load, we have stresses that are built up inside, and at some point, if we overstress an object, it's going to break. So in order for us to predict failures, we have to be able to understand what are the loads that are built up inside of a beam, and that's what we do in this section. So we're going to look at what are the loads in terms of forces and other things that are built up inside of beams at any given point, and then understand what factors go into creating stress in a beam. So when we talk about a failure of a beam, we have two different ways that a beam's going to fail primarily. So we have a case where a beam is going to bend. So we have flexion that happens, and we would have either an upwards bend or a downwards bend and could lead to a failure. Or else what we might have is a shearing failure. So we have a case where our object is going to break straight up or straight down, and we have that sliding failure. And we can predict these types of failures in materials if we know what sort of stresses and what sort of forces these objects are under. So in the last video we looked at cantilever beams, and when we find the reaction forces in a cantilever beam, we went through the same sort of approach that we're going to go through when we look at internal loads. We went through a strategy where we cut the beam at the wall. So we removed the wall, in that case was the left-hand portion of the beam that was embedded in the wall, and we then just replaced that with forces. And when we replaced it with forces, we replaced it with an up force, that was the wall's reaction holding up the beam, and we replaced it with a moment, again, that the wall was holding up the beam. But that wasn't really what the wall was doing. All it was doing was what was happening on the end of the beam that meant that it was kept in equilibrium. And actually what was happening was it wasn't the wall, it was the different sections of the beam. So the left-hand side of the beam that remained in the wall was holding up the right-hand section of the beam that was extended away from the wall. And it's the material of the beam that holds it all together, so those bonds and those atoms. Whenever we put a section under load, so for instance on the left-hand side we put some sort of shearing load, an up and down force on that section of atoms, we're going to create a little bit of a stretch. And if that stretch continues, we may break that bond. And that's when we would have a failure. So when we have that stretching, we know that a change in dimensions is going to be what we call strain. And if that strain becomes too much, it's going to create a large stress, and we're going to create a failure. If we look at one individual slice, in order for me to be able to create that shearing, I have to have equal and opposite forces. And if I look at not just the whole beam itself, but I look at any individual section, if it's going to be in equilibrium, I have to have equal and opposite forces acting at every point. And we can think of it this way. If the entire beam is in equilibrium, it means that every atom, slice, or section of the beam is also going to be in equilibrium. So by virtue of the fact that the whole thing is in equilibrium, any little slice or sliver or section or part of the beam that we look at, we can also consider to be in equilibrium. And that's a really important thing for us, because what happens next is when we want to find out what are those forces, then we have a method that we can use to find them. So what we do is we essentially slice a beam just like we did with the cantilever beam at the wall. And we replace the beam with the equivalent load that those bonds between the atoms are creating. And what we do in this case is we replace with a V, which is the convention that we use for shear, and we replace with an M, which is what we use to represent moments. And so just like we have a cantilever beam, when we cut it, we replace both sides. And we talked about beam connection types, and one of them was the fixed type. And so basically we can think that this beam is fixed left-hand side to right-hand side by virtue of those bonds in between. The V and the M that we have at the slice, what's really important about them is that they are the same magnitude. So for it to be in equilibrium, and we looked at that slice, we'd have to balance those V's. And in order for that to happen, they have to be equal in the magnitude, but opposite in direction. The M's, sometimes you don't notice that they're in opposite directions, but remember that we don't talk about M's in ups and downs, we talk about them in clockwise or counterclockwise, and we can see that the M in the left-hand side section is going in the counterclockwise direction, whereas the M on the right-hand side is going in clockwise. So the M's are equal in magnitude but opposite in direction. The V's are opposite in direction and equal in magnitude. And the net result is that those sections, the left-hand side with those bonds in place, or those forces in place, it is in equilibrium. So if I want to find out what is the magnitude of the shear and bending moment halfway along the beam, so what would V or M be? Well, let's work ahead and see if we can calculate that. Okay, so let's work away at this problem. What is the magnitude of the shear and bending moment halfway along the beam? So at the halfway point, somewhere out here, I'm going to cut the beam. Before I go to the point of looking at the internal loads and cutting the beam, what I want to do is I want to make sure that I know all of the external loads that are acting on this beam. And so I've provided that to you, 120 and 80. However, if you don't know that information, you need to go back to what we did in the previous parts, find out any unknown external loads. We need those in order to be able to find what's happening inside the beam. Okay, so since I have that, what we're going to do is we're going to cut this beam. And we're going to cut it into a left-hand side section. And we're going to cut it into a right-hand side section. Okay. Now, since the entire beam itself was in equilibrium, it means that both my left-hand side and my right-hand side of the beam are also going to be in equilibrium. And so, because they're in equilibrium, I need some forces that I'm going to put in there to make sure that they are in equilibrium. So at the cut, I'm going to consider it to be like a cantilever beam or a fixed point. And the fixed point is going to have two forces. One, I'm going to have an M, and in addition, I'm also going to have a V. Okay, so a force, a V, and a moment, M. And I'm going to complete the rest of the object. So I have 100 that's pushing down, and I have 120 that's pushing up. And I guess if this whole thing, the whole beam looks to be 5 meters, so the entire left-hand side would be half, 2.5. And I may want to go and do some measurements at some point to understand exactly where that 100 Newton force is, but I do know, it's at a distance of 1 meter here. Okay, so that's my left-hand side. My right-hand side, same thing. I could replace at the joint with a V and an M. Now, since I've already assigned my V going down, I'm going to assign the V going up at this joint. And I'm going to assign my M going clockwise because I assigned the M going counterclockwise at the other side of that joint. 100's going to push down, and I have 80 that's pushing up. Whole thing is 2.5 meters as well. And looks like the 100 is 2 meters from the 80. 2 meters. Okay, and so I have my left and my right hand side, and both of them are in equilibrium. Okay. At this point, if I want to calculate V and M, just like I did with a cantilever beam, I would follow the same steps as I did in part number 2. So in this case, I can pick either the left-hand side or the right-hand side to evaluate. It doesn't matter which one. Sometimes one of them looks easier than the other, and I may choose that if it has fewer forces or other things. But it looks like these guys are about equal. So just out of space, I'm going to evaluate my right-hand side, and let's just take a look. So same thing I did with my cantilever beam. I have free body diagram. I've got my V, I've got my M. I have my 100 pushing down, and I have 80 pushing up. I assign my reference point or my pivot point on a cantilever beam as the wall, or more specifically where I've made my cut. And I'm going to repeat that same process. So I have my reference point here at the cut. Okay, so I also encouraged you, we should find all of our dimensions from the cut. So going across to the 100, in this case, it's going to be 2.5 minus 2 meters, so that guy would be 0.5 meters. Across to the 80 is going to be 2.5 meters. And I think I have all my information that I need. So again, with a cantilever beam, it doesn't matter if I do forces up or moments first. So usually my preference is to do forces. So all the forces going up have to balance all the forces going down. V plus, well, I'll just work my way across. So I got V going up. I have 100 going down. And I have 80 going up. So 80 on this side. And I could solve to say V is equal to 20. And I guess that would be units of newtons. Okay. Sum of moments in one direction has to equal my sum of moments in the opposite direction. And I just noticed I didn't label this guy as M, but that's going to be an important one to know. So if as I go across, I'm going to start at my point and work my way across. So my reference point, I have an M, and it is in the clockwise direction. Okay. Work my way across. I have the 100, it's also in the clockwise direction. Oops. And it's at a distance of 0.5 meters. And complete my way all the way across, and I have an 80 that is going in the opposite direction. So I have 80 at a distance of 2.5. So M plus 50 Newton meters is going to be equal to 80 times 2.5, yes, it's 200. Newton meters, and M is going to be equal to 150 Newton meters. Okay. So this tells me what forces are acting at that interface. Okay, so what is built up inside of the material that's holding it together, allowing it to be in equilibrium internally. And I found some values there. So I found my V and my M. And had I used my left-hand side, so if I had gone through the calculation with that guy, I would have found that V is equal to 20 newtons, M is equal to 150 Newton meters, and I would have the exact same answer as I did with the other side. So no matter which side we look at, we should have the same V and M, because once again, they're the same magnitude as each other, and that's the only way that we can have equilibrium at that point. Okay. Now we don't always have to look at the midpoint of these beams, so we could look at different points. So for instance, maybe I want it to look at a point over here. I think that that might be a risk to break, or a point over here. And so I could make a number of little slices along there, break it up into a left or a right hand side, draw my V and my M, and then continue on either evaluating the left or the right hand side as if it was a cantilever beam. So let's take that same beam and now ask ourselves, we looked at it in the middle, what would happen if we looked at a different point? So why don't we look at what is the internal load at the 100 Newton point load on the right hand side? So if we sliced it there, what would be our V and M, the internal loads at that point? Okay, so we're going to take the same approach. I'm going to slice it right down that slice. Great, and I'm going to draw my left hand side. So there's my left hand side, and I'm going to draw my right hand side. Okay. So I'm going to assign, just like I did before, a V, and I'll assign equal and opposite on both, and an M, so equal and opposite on both. And I'll draw in the rest of the stuff I know, so 80, I got 120, those are my reactions. I have 100 pushing down over here, and then, I'm not sure what to do here. I have my cut that's happening right at a point load, and I'm not 100% sure what to do. So we have to make a decision here. It's got to go on one side or the other, so I can't cut it right down the middle, so it's not 50 on one side or the other, 100 on either side. So why don't I just make a guess that it's on this side, which means over on the left hand side it would be 0. Okay, so if I evaluate it my right hand side, it's my right hand side, so sum of forces up has to equal forces down. Pushing up, V plus 80 is equal to pushing down is 100. So similar to the last time, we had V is equal to 20 newtons. We also have our sum of moments. One direction has to equal our sum of moments in the other direction. My whole section of beam is 2 meters in length. I take my reference point as the cut, which means both V is at a distance of 0 and 100 is at a distance at 0. So those guys won't create a moment. However, I got to make sure I don't forget M. M is at the cut, so M is there, and M is going to be equal to 80 times 2, and M in this case would be 160 Newton meters. Okay, so that's one approach that I could take. However, if I took the approach that I didn't have 100 here, so let's say I didn't have 100, and let's say I had 0, and my 100 was actually over on the left-hand side. Let's see what happens. So in this case, now with the 100, or with 0 as the force, and with the 100, I guess, at the interface. So same thing, forces up has to equal my sum of forces down. I have V again up, and I also have an 80 up, and is equal to, well, I had 100 that I was pushing down before, but it's not there anymore, so I guess that's just 0, and V is equal to negative 80 newtons. My sum of moments in one direction has to equal my sum of moments in the opposite direction. At the point, my reference point, I have an M. V is going to be multiplied by a distance of 0, so it disappears, and it's going to be equal to 80 at a distance of 2. In this case, M is equal to 160 Newton meters. Okay. So we can see a couple things right here. First of all, there are two answers for V. And this is a little strange, but both are correct. Depending on which side of that force we're sitting on, we would see that much V. We're in a transition zone, so that point load is changing my V fairly drastically. So I have lots of V shearing that's happening at one side, and then shearing in the opposite direction at the other side, so the positive and negative. So we have two answers for V whenever we're at a point load. And if we look at what's happening with our M, we always are going to have one answer for M. It's unchanged. So what happens if we look at a section, or creating a section where there is a point load? So if there's a point load, you can include it or not in your calculation. And what that means is that really there's two possible answers for V at that point. So usually if you give me one or the other, that is acceptable in our testing. But just be aware, if you're asked on a TSSA exam and it's a multiple choice, if you're not getting the V that you're expecting, then it might be because it's at a cut and you need it to include it.